The Kennedy Space Center regularly hosts an event that attracts thousands of people from around the world.
-10, 9, 8, 7, 6, go for engine start. 4, 3, 2, 1, 0, and liftoff of Space Shuttle Endeavour.
The sight and thunderous sound of a NASA shuttle launch is one of the most stunning and dramatic events witnessed on Earth. The NASA Space Shuttle has come to represent mankind's transition from bold newcomers to space exploration to pioneering scientists carrying out invaluable research to benefit our understanding of space and of our planet. Although the NASA Space Shuttle program is winding down its prestigious career of nearly 30 years service, it will live long in the memory of young and old alike. Representing the pinnacle of mankind's technological achievements, it is the product of decades of scientific research and advancements made in the field of space travel. The shuttle is unlike any other vehicle in history. It is truly a design icon. The concept of a winged reusable spacecraft began before the beginning of the space race in the 1960s, even before the Apollo moon landing in 1969. Following the Apollo space program, NASA officials were looking to the future of space exploration. In previous missions, disposable rockets were used, and the idea of a reliable and reusable, less expensive rocket was considered. The space shuttle would launch like a conventional rocket, but would be able to land like an airplane. This concept will be considered an incredible technical achievement. The military position of the United States following the close of World War II was one of superiority. Mainly due to advancements in weapon technologies, a large strategic bomber force, and military bases that were close to Soviet territories. In response to this, and to the state of conflict between these two powerful nations, the Soviet Union was to make the advancement of rocket and long-range missile technologies a key priority. Although the motive behind these developments was military use, it soon became clear that the same technology that allowed missiles or rockets to threaten the world's safety would open the doors for space travel. On the 4th of October 1957, the Soviet Union launched the first man-made object beyond the Earth's atmosphere and into space. The satellite, named Sputnik 1, was the first of a series of satellites to be launched as part of the Soviet Sputnik program.
I was 9 years old. I remember the announcement. They said at night you could see Sputnik in a certain direction, from the southeast. We saw it, but we were surprised it wasn't bright or shiny.
It was the successful launch of the world's first artificial Earth-orbiting satellite and was to surprise the United States, who believed at the time to be the world leader in space technology. The Sputnik satellite was astonishingly small in its design. At 58 centimeters in diameter, it was about the size of a beach ball and weighed in at only 83.6 kilograms. Its construction consisted of two hemispheres that were covered in a highly polished heat shield of aluminum, magnesium and titanium. The United States, prior to the launch of Sputnik 1, had announced its intentions to launch similar artificial satellites as part of the Project Vanguard. It was during early testing that the Project Vanguard team learnt of Sputnik 1 and its successful launch. The failed launch of Vanguard TV3 at Cape Canaveral on December 6, 1957, meant that the US were not able to immediately equal the Soviet efforts.
Neither the satellite program nor our missile development is affected, said Acting Defense Secretary Quarles. It's only an incident in the perfection of the Vanguard satellite system.
In response to the events surrounding the launch of Sputnik 1, and in an attempt to close the technical gap that the United States clearly felt existed between its space program and the Soviet Union's, US President Dwight Eisenhower and his administration passed several initiatives that would hopefully push forward the US space program. Amongst these initiatives was the signing of the National Aeronautics and Space Act on July the 29th, 1958, creating the agency that would be responsible for the United States public space program, NASA. On February the 1st, 1958, the US launched its first successful satellite, Explorer 1, and became the world's second space power.
After two much-publicized failures, Project Vanguard scores a bullseye on its third firing at Cape Canaveral. A grapefruit-sized satellite is set into the nose cone of a three-stage rocket, and the launching routine begins. The countdown goes with amazing ease, even faster than that of the Jupiter C. Only 16 seconds off a precision schedule, the Vanguard blasts off. It's one of the most perfect flights ever seen at the Missile Center, and there's not a hitch along the way, as the tiny moon is catapulted into the farthest orbit yet, 2,500 miles out. This launching was basically an experiment to test the rocket's flight pattern, preparatory to the launching of a 21-inch satellite later this year. Successful orbiting of a 6-inch moon was sheer profit as far as the engineers were concerned, making the first good news from Project Vanguard very good news indeed for all America. At Cape Canaveral, the 7 United States Project Mercury astronauts are among the observers at the firing of a Redstone rocket carrying an unmanned space capsule. The capsule, called the MR-1A, is an exact replica of what will be America's first man-in-space capsule. After the flawless launching, the carrier rocket heads down the Atlantic firing range until it burns out and separates from the capsule, which travels 135 miles further out into space before returning to Earth.
Project Mercury was the first human spaceflight program of the United States. It ran from 1959 through 1963 with the goal of putting a human in orbit around the Earth. The first to achieve this objective was the Mercury Atlas 6 flight on the 20th of February 1962. Early planning and research was carried out by the National Advisory Committee for Aeronautics, and the program was officially conducted by the newly created NASA. Because of their small size, it was said that the Mercury spacecraft were worn, not ridden. With 1.7 cubic meters of habitable volume, the spacecraft was just large enough for a single crew member. Inside were 120 controls, 55 electrical switches, 30 fuses, and 35 mechanical levers. The man in charge of designing the Mercury spacecraft was Max Faget, who would go on to design the Gemini and Apollo crafts and later oversee the iconic shuttle spacecrafts. The Mercury spacecraft were designed to be completely controllable from the ground in the event that something impaired the pilot's ability to function. The program included 20 unmanned launches, not all intended for space and with limited success. 4 of these flights included non-human primates, starting with the 5th flight, 1959, which launched a rhesus macaque named Sam, named after the Air Force's School of Aerospace Medicine. During this time, Russia had overtaken America and was successful in sending a human into orbit. On the 12th of April 1961, Yuri Gagarin became the first human to travel into space, launching to orbit aboard the Soviet craft Vostok 1. The first Americans to venture into space were drawn from a group of 110 military pilots, chosen from their flight test experience and because they met certain physical requirements. Alan Shepard became the first American man into suborbit aboard Mercury Redstone 3 on the 5th of May 1961.
Yes, sir. Reading it loud and clear. This is Freedom.
Almost a year later, John Glenn became the first American into orbit aboard Mercury Atlas 6, amid many concerns about man surviving in zero-gravity conditions. Within weeks of Shepard's launch, President Kennedy publicly committed to land man on the moon within 10 years and returning him.
This country was conquered by those who move forward, and so will space. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
And thus, by the 13th of June 1963, NASA had now successfully sent 6 men into orbit on 6 separate manned launches. Project Gemini was the second human spaceflight program of the National Aeronautics and Space Administration. With 10 manned flights occurring in 1965 and 1966, its objective was to develop techniques for advanced space travel. The advances made on Gemini would later be used to put a man on the moon and in the design of the Space Shuttle program. The major objectives assigned to Gemini were to subject 2 crew members and supporting equipment to long-duration flights, to effect rendezvous and docking with other orbiting vehicles, and to maneuver the docked vehicles in space using the propulsion system of the target vehicle for such maneuvers, to perfect methods of re-entry and landing the spacecraft at a pre-selected landing point, to gain additional information concerning the effects of weightlessness on crew members and to record the physiological reactions of crew members during long-duration flights, to accomplish EVA, extravehicular activity, or spacewalks outside the protection of the spacecraft. Unlike Mercury, which could only change its orientation in space, the Gemini spacecraft could alter its orbit. It could also dock with the Agena target vehicle, which had its own large rocket engine and was used to perform large orbital changes. Gemini was the first American manned spacecraft to include an onboard computer, the Gemini Guidance Computer, to facilitate management and control of mission maneuvers. It was also unlike other NASA aircraft in that it used ejection seats, in-flight radar, and an artificial horizon, devices borrowed from the aviation industry. Ejection seats were first used on board Vostok 1 during Yuri Gagarin's flight.
Houston at last, runways in sight.
The Apollo program was the third program, a human spaceflight program undertaken by NASA during the years 1961 to 1975, with the goal of conducting manned moon landing missions. In 1961, President John F. Kennedy announced a goal of landing a man on the moon by the end of the decade.
2, 1, 0, all engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
Neil Armstrong reporting the roll and pitch program, which puts Apollo 11 on proper heading. Houston, Apollo 11 is calling you in the high gain. How do you read, over? Roger, loud and clear on the high gain. Eagle, you're looking great. Coming up 9 minutes. We're now in the approach phase. Everything looking good. Altitude 42. Houston, you're go for landing, over. 40 feet down, 2.5. Picking up some dust. 30 feet, 2.5 down. Straight shadow. 4 forward. 4 forward, drift into the right low. 6, down a half. 30 seconds forward. Good. 8, 7, 6, 5, 4, 3, 2, 1, Kennedy Base here. The Eagle has landed. That's one small step for man, one giant leap for mankind.
It was accomplished on July the 20th, 1969 by the landing of astronauts Neil Armstrong and Buzz Aldrin, with Michael Collins orbiting above during the Apollo 11 mission. Five subsequent Apollo missions also landed astronauts on the Moon, the last one in 1972. To this day, the 6 Apollo spaceflights are the only times humans have landed on another celestial body. The goal of the program, to land on the Moon and return, was accomplished with only 2 major setbacks. The first was the Apollo 1 launchpad fire that resulted in the deaths of astronaut Gus Grissom, Ed White and Roger Chaffee. The second was an in-space explosion on Apollo 13, which badly damaged the spacecraft on the moonward leg of its journey.
Okay, Houston, we've had a problem here.
Flight guidance. Go guidance. We've had a hardware restart. I don't know what it was.
From the start, the exploration of space has been hazardous adventure. The voyage of Apollo 13 dramatized its risk. The men of Apollo 13, by their poise and skill under the most intense kind of pressure, epitomize the character that accepts danger and surmounts it. Theirs is the spirit that built America.
The Apollo program set major milestones in the history of human spaceflight. Apollo stands alone in sending manned missions beyond low Earth orbit. Apollo 8 was the first manned spacecraft to orbit another celestial body, while Apollo 17 marked the last moonwalk and the last manned mission beyond low Earth orbit. In 1969, President Richard Nixon formed the Space Task Group, chaired by Vice President Spiro T. Agnew. This group evaluated the shuttle studies to date and recommended a national space strategy, including building a space shuttle. The goal, as presented by NASA to Congress, was to provide a much less expensive means of access to space that would be used by NASA, the Department of Defense, and other commercial and scientific users. On January 5, 1972, the shuttle program was formally launched. NASA would proceed with a brand new and reusable space shuttle system. The winged Space Shuttle orbiter is launched vertically, carrying up to 8 crew and up to 25 tons of payload into low Earth orbit. When its mission is complete, the shuttle can independently move itself out of orbit and re-enter the Earth's atmosphere. During descent and landing, the orbiter acts as a re-entry vehicle and a glider, and lands on a runway much like a standard aircraft, with the ability to do it again and again. The orbiter structure is made primarily from aluminum alloy, although the engine thrust structure is made from titanium alloy. The windows are made of aluminum silica glass and fused silica glass. The shuttle has neither anti-collision, navigation nor landing lights. When landing at night, the runway is flooded with light from ground spotlights. The Space Shuttle comprises of several main sections. The orbiter resembles a conventional aircraft, with double delta wings swept 81 degrees and 45 degrees at the outer leading edge. Its vertical stabilizer's leading edge is swept back at a 50-degree angle. The 4 elevons mounted at the trailing edge of the wings and the rudder speed brake attached at the trailing edge of the stabilizer control the orbiter during descent and landing. The orbiter has a massive payload bay measuring 15 by 60 feet, comprising most of the fuselage. The crucial factor in the size and shape of the shuttle orbiter was the requirement that it be able to accommodate the largest planned commercial and classified satellites. The orbiter can also recover satellites and other payloads from orbit and return them to Earth. 3 Space Shuttle main engines are mounted on the orbiter's aft fuselage in a triangular pattern. The 3 engines can swivel 10.5 degrees up and down and 8.5 degrees from side to side during ascent to change the direction of their thrust and steer the shuttle as well as push. 2 solid rocket boosters mounted each side of the orbiter and external tank provide 12.8 million foot-pounds of thrust at liftoff, which is 83% of total thrust needed for liftoff. The Space Shuttle program occupies over 654 facilities, uses over 1.2 million line items of equipment, and employs over 5,000 people. 6 airworthy Space Shuttle orbiters have been built. The first complete orbiter was originally planned to be named Constitution, but a massive write-in campaign from fans of the Star Trek television series convinced the White House to change the name to Enterprise. Amid great fanfare, Enterprise was rolled out on September 17, 1976, and later conducted a successful series of glide approach and landing tests that were the first real validation of the design. 5 spaceworthy orbiters were built: Columbia, Challenger, Discovery, Atlantis, and Endeavour. The first fully functional orbiter was the Columbia. It was delivered to Kennedy Space Center on March 25, 1979, and was first launched on April 12, 1981, the 20th anniversary of Yuri Gagarin's spaceflight, with a crew of 2. Challenger was delivered to KSC in July 1982, Discovery in November 1983, and Atlantis in April 1985. Challenger was originally built and used as a structural test article, but was converted to a complete shuttle when NASA found this to be less expensive than converting Enterprise from its approach and landing test configuration. Endeavour was built to replace Challenger, using structural parts originally intended for other orbiters and delivered in May 1991. It was first launched a year later. Out of the 5 fully functional shuttle orbiters built, 3 remain. Over the years, the orbital fleet has received many upgrades. Internally, the shuttle remains largely similar to the original design, with the exception of the improved avionics computers. In addition to the computer upgrades, the original analog primary flight instruments were replaced with modern full-color flat-panel display screens, similar to those on contemporary commercial airliners. With the coming of the International Space Station, the orbiter's internal airlocks have been replaced with external docking systems to allow for a greater amount of cargo to be stored on the shuttle's middeck during station resupply missions. By the time the shuttle fleet retires, 134 missions will have been completed, over 35 separate missions to the International Space Station, and 4 missions to service the Hubble Space Telescope, as well as many more. The legacy of the Space Shuttle era will continue to flourish for many years to come. NASA's shuttle program has not been without its problems. 2 fatal accidents remind us that our ventures into space are not without their dangers. The spacecraft disintegrated over the Atlantic Ocean, off the coast of central Florida. Disintegration of the entire vehicle began after an O-ring seal in its right solid rocket booster failed at liftoff. The O-ring failure caused a breach in the SRB joint it sealed, allowing pressurized hot gas from within the solid rocket motor to reach the outside and impinge upon the adjacent SRB attachment hardware and external fuel tank. This led to the separation of the right-hand SRB's aft attachment and the structural failure of the external tank. Aerodynamic forces promptly broke up the orbiter.
We have a report from the flight dynamics officer that the vehicle has exploded. Flight director confirms that. We are looking at checking with the recovery forces to see what can be done at this point.
The disaster resulted in a 32-month hiatus in the shuttle program and the formation of the Rogers Commission, a special commission appointed by United States President Ronald Reagan to investigate the accident. The commission concluded that the Challenger disaster was an accident rooted in history. After the accident, NASA's Space Shuttle fleet was grounded for almost 3 years, whilst the investigation, hearings, engineering redesigns of the SRBs and other behind-the-scenes technical and management reviews, changes and preparations were taking place. On September the 29th, 1988, Space Shuttle Discovery lifted off with a crew of 5 from Kennedy Space Center. The return to flight launch of Discovery also represented a test of the redesigned boosters, a shift to a more conservative stance on safety, and a chance to restore national pride in the American space program, especially manned spaceflight. The mission, STS-26, was a success, and a regular schedule of STS flights followed, continuing without extended interruption until the Columbia accident. 17 years after Challenger, Columbia was lost, shortly before it was scheduled to conclude its 28th mission, during re-entry on February 1, 2003, and it has not been replaced.
Booster ignition and liftoff of Shuttle Discovery. Combate Kudasai. Best of luck to the International Space Station's newest laboratory.
Houston, Discovery, roll program.
Roger, roll, Discovery. Houston.
36.
Space shuttles have been instrumental in the construction and development of the International Space Station. Shuttle missions provide resupply missions, assembly and logistics flights, and crew rotation. On the day of a launch, after a final hold in the countdown at T-9 minutes, the shuttle goes through its final preparations for launch. And the countdown is automatically controlled by the ground launch sequencer software at the Launch Control Center, which stops the count if it senses a critical problem with any of the shuttle's onboard systems. The GLS hands off the count to the shuttle's onboard computers at T-minus 31 seconds in a process called Auto Sequence Start.
GLS is go for Auto Sequence Start.
25.
And we have a go for Auto Sequence Start. Discovery's onboard computers have primary control of all the vehicle's critical functions.
15.
At T-minus 16 seconds, the massive sound suppression system begins to drench the launch platform and SRB trenches with 300,000 gallons of water to protect the orbiter from damage by sound energy and rocket exhaust during liftoff. At T-minus 10 seconds, the main engine turbo pumps begin charging the combustion chambers with liquid hydrogen and liquid oxygen at this time. The computers reciprocate this action by allowing the redundant computer systems to begin the firing phase. The 3 Space Shuttle engines start at T-minus 6.6 seconds. After the main engines start, but while the solid rocket boosters are still clamped to the pad, the offset thrust from the shuttle's 3 main engines causes the entire launch shuttle to pitch down about 2 meters at cockpit level. This motion is called the nod. As the boosters flex back into their original shape, the launch stack pitches slowly back upright. This takes approximately 6 seconds. At the point when it is perfectly vertical, the boosters ignite and the launch commences.
1. Booster ignition and liftoff of Endeavour, completing Kibo and fulfilling Japan's hope for an out-of-this-world space laboratory.
Shortly after clearing the tower, the shuttle begins a roll and pitch program to set its orbital inclination and so that the vehicle is below the external tank and SRBs, with wings level.
Roger, roll, Atlantis.
Atlantis' roll maneuver is complete. The orbiter's in a heads-down position, on course for a 51.6 degree, 137 by 36 statute mile orbit.
The shuttle climbs in a progressively flattening arc, accelerating as the weight of the SRBs and the main tank decrease.
One minute 45 seconds into the flight.
2 minutes after launch, the solid rocket boosters are separated from the shuttle. The SRBs parachute back to the ocean to be reused.
Discovery 22 miles in altitude, 23 miles downrange, standing by for solid rocket booster separation.
Copy staging.
Booster officer confirms staging, a good solid rocket booster separation.
There's a tremendous rush involved with this particular experience, as you might imagine.
The shuttle then begins accelerating to orbit on the Space Shuttle main engines.
8.5 minutes later, we were in orbit. I asked if I could open my eyes yet, and this is what one sees when you do open your eyes. It's a beautiful, beautiful sight.
Well, at the risk of endorsing the product, that's an interesting physical demonstration on orbit of the fact that it's done really on weightless.
Our first task, of course, was to deploy Telsat. It was a nighttime deploy, and so this is a TV picture, nighttime TV picture of the deploy. It looks more or less like in the day. You just can't see it too well. Went smoothly.
This is Blue Ashmo talking now, and there you can see myself and Steve Swanson setting up for one of our mid-course correction burns and moved to the rendezvous this morning. And what you saw right there was Daniel Levis just checking out his handheld laser. And here you can see our commander, Rick Sturko, getting an ID on the space station through his COAS. And that's what the station looked like coming up to it. Again, it's myself and Steve Swanson still performing or getting ready to perform one of our mid-course correction burns. We did 4 of those today en route to the rendezvous. Another requirement we have as we approach is to do photo documentation, do a complete coverage of the station, and we would doing that with those 2 cameras.
Okay, we're doing the RPM maneuver right now, and this is looking at the station at the forward window, which is kind of an interesting place to see it. The reason we were doing this is so that the station crew could take pictures of the RCC and the tiles on the shuttle's belly.
To achieve low orbit requires much more horizontal and vertical acceleration. The near circular orbital velocity at the 236 miles altitude of the International Space Station is 17,000 miles per hour, roughly equivalent to Mach 23 at sea level. As the International Space Station orbits at an inclination of 51.6 degrees, the shuttle has to set its inclination to the same value to rendezvous with the station.
We are very happy when we were completing the RPM. You can see the station came up pretty much centered on the orbiter's tail, which was a good sign. So we are completing the RPM, and now the station is back where we're used to seeing it in the overhead windows. Here you can see JR doing some more documentation with the 400 millimeter lens of the station exterior. Danny is making handheld laser marks and Bruce backing everything up on the checklist procedures and entering the orbiter attitudes on the universal pointing display.
After we have docked, we use the APDS system. It pulls the station and shuttle together, and after we have a good seal, a series of latches and hooks. And this is a picture of JR getting ready to open the hatches. He has to do some prep work first before we do. Here he is opening the hatch at this time. And there's JR waving hello to Fyodor, Oleg, and Sonny. And next is the crew going through the adapter, the PMA-2, and into station. With greetings to the ISS crew. And that's Commander Rick Starkow giving presence to the current expedition crew.
We are the experiment.
The International Space Station's main purpose is to provide a platform in space for research, an orbiting laboratory, and the largest satellite ever to be launched into orbit. On-orbit construction of the International Space Station began in 1998 and is not expected to be complete until 2011. Space Shuttles Discovery, Atlantis and Endeavour delivered the Destiny Laboratory and Quest airlock to orbit, in addition to the station's robot arm and several more segments of the truss structure. The expansion schedule was brought to an abrupt halt, however, following the destruction of the Space Shuttle Columbia on STS-107 in 2003. The resulting hiatus in the Space Shuttle program halted the station assembly until the launch of Discovery on STS-114 in 2005. The official return to assembly was marked by the arrival of Atlantis, delivering the station's second set of solar arrays. These were later followed by several more truss segments and a third set of arrays. This major expansion of the station's power generating capabilities meant that more pressurized modules could be accommodated. And as a result, the Harmony Node and Columbus European Laboratory were added. These were followed shortly after by the first two components of Kibo, the Japanese experiment module. In March 2009, Discovery marked the completion of the integrated truss structure with the installation of the fourth and final set of solar arrays, whilst the final section of Kibo was delivered by Endeavour in July 2009. With thanks to the shuttle, the ISS is now a permanently manned station, with crews cycling regularly on the three craft.
Riding on a spaceship.
The ISS is a long-term platform in space, providing a constant human presence beyond Earth's atmosphere for the past 8 years. It is precisely this ability to provide long-duration studies in space that makes the space station better suited to its purpose than spacecraft like the NASA Space Shuttle. Further operations on the space station will take place until 2015. The space station sits at a low Earth orbit, approximately 220 miles above the Earth's surface, and travels at an average speed of 17,000 miles per hour. Seen from the Earth with the naked eye, the ISS completes 15.7 orbits of the Earth daily. The station consists of a number of pressurized modules and unpressurized components, which were launched by the Space Shuttle, Soyuz rocket or Proton rocket. It has been visited by astronauts from 16 different nations and is serviced by many manned and unmanned spacecraft. Research on the space station is conducted on a daily basis and consists of human research, life sciences, physical sciences and Earth observations.
This is a surprise visit that you guys are paying on us today. So things aren't cleaned up, but they're real. This is exactly how we work and live in space. Okay, here we are at the very front end of the International Space Station. This is the forward end of Node 2. And this is right behind this hatch is the PMA, the pressurized mating adapter, to which the space shuttle docks whenever the next space shuttle comes. You can see we have our flags up here at the most forward part. It's a 15-nation partnership, this International Space Station. Welcome to Kibo. Please enjoy and relax in this brand new, the most spacious and quietest room in the ISS. You can see here, this is the SIBO rack, which is for cell biology. And then we have a fluid rack, Urutai. So these are the two main Japanese science racks that are up here now. There's more that are coming. Oh my goodness, it's beautiful up there. So this is looking out the port side of the space station. Here we are in the Columbus module. You can see it's also spacious. It's also cluttered because it's a great place to store things or temporarily stow them. It's not going to be this way forever. We're going to have it nice and clean pretty soon. First and foremost, we are now in the pressurized adapter part of the functional cargo block. We call it the GAA, and it's also a docking port down below. As you carefully look down below, you can see the hatches, and inside what you can see in front of us is the docking mechanism for the Soyuz. And this is the hatch that I opened up and went outside for a spacewalk, and we're looking aft on the space station. There's a ladder.
Scientific findings are published every month. The International Space Station program allows 14 different nations to live and work together in space and represents a multinational future for space exploration.
Discovery International Space Station, the President of the United States.
Hello, Commander, can you hear us? Oh, I got it.
President, welcome aboard the International Space Station, where we're joined with our international crew from the Space Shuttle Discovery. Welcome aboard. Glad to hear your voice. We hear you loud and clear, sir.
Well, thank you so much for taking the time to speak with us. We've got a crew of wonderful school children here who are all interested in space, and we've got some members of Congress who are like big kids when it comes to talking to astronauts. I'm told that you're cruising at about 17,000 miles per hour, so we're glad that you are using the hands-free phone.
Mr. President, we go around the planet once every 90 minutes. It's quite a thrill, and it is very fast, and we see 16 sunrises and 16 sunsets every day.
Well, obviously, we're really proud about the extraordinary work that our American astronauts are doing. You know, you are a representative of the dedication and sense of adventure and discovery that we're so proud of. But one of the things that's wonderful about this is that it is an international space station, and I know that we have our Japanese and Russian counterparts on board as well. We'd love to say hello to them and hope that that this is an example of the kind of spirit of cooperation that we can apply not just in space but here on the ground as well. Tell us what kinds of experiments are you doing? Once you got the panel up, what kinds of other activities are you doing? Is it mostly just maintaining the craft, or are there certain experiments or projects that you're engaged in as well?
Well, sir, we have experiments already up here that we've been doing for many years, and we'll be able to double that with the addition of the solar array that our shuttle friends brought up. We do a lot of experiments on combustion, understanding materials, understanding how, we're guinea pigs, so understanding how people's bodies change in space, and all this is in preparation for long-duration missions to Moon and Mars. And the exciting thing about doing science up here is we really don't know what we don't know, and that gives you the greatest potential for learning. And we've had a lot of cases where people have set up experiments, and we've conducted them here on the space station, only to find out that we've learned something new, something more about the fundamentals of the processes and the science. So it's a really great place to learn a lot.
Last but not least, in the service module, Zvezda, which means star. It's the heart of the space station. It's where we used to have the only place where we could create oxygen and live with the carbon dioxide removal system, as well as a place to eat and sleep. There's my crewmate, Yuri Lonchikov, exercising on the treadmill with vibration isolation system, the TVIS. So, this is our eating area. There's our table. And we're just getting ready for lunch. There's our water dispenser right there, Russian style. And that'll wrap up the tour. This is the International Space Station. A very good example of what human beings can do when we work closely together.
Remarkably, the Space Shuttle is still the only winged manned spacecraft to achieve orbit and land, and the only reusable space vehicle that has ever made multiple flights into orbit. The Space Shuttle orbit vehicle was designed with a reusable heat shield for use on re-entry. A space shuttle's underside is coated with thousands of tiles made of silica foam, which are intended to survive multiple re-entries with only minor repairs between missions. Fabric sheets known as gap fillers are inserted between the tiles where necessary. These gap fillers provide for a snug fit between separate tiles while allowing for thermal expansion. When a space shuttle lands, a significant amount of heat is stored in the thermal shield. The final approach and landing phase can be controlled by the autopilot, but is usually hand-flown.
4 minutes to touchdown. Commander Penn Miller has taken over the flight of the Space Shuttle Discovery, flying at 600 miles per hour at an altitude of 44,000 feet.
Houston, Discovery, post-landing, MTS reconfig, still in work.
Almost the entire Space Shuttle re-entry, except for lowering the landing gear and deploying the air data probes, is normally performed under computer control.
Discovery's landing gear is down and locked in place. Main gear touchdown. Commander Penn Miller is rotating the nose gear down to the runway and nose gear touchdown. Discovery is rolling out on runway 33 at the Kennedy Space Center, wrapping up a 6.25 million mile mission. Discovery completing its 34th mission to space and the 23rd shuttle flight to the International Space Station.
Space Shuttle landings are always planned for Kennedy Space Center. If weather conditions make landing there unfavourable, the shuttle can delay its landing until conditions are favourable, touchdown at Edwards Air Force Base, California, or at other sites around the world.
Houston, Discovery will stop.
Copy, we'll stop Discovery. Congratulations on a tremendous mission and a great landing, Pam. And we'll meet you on page 5-3 with no deltas.
Technological advances gained as part of the shuttle program over its life continues to find its way into our everyday lives, in homes, hospitals, schools, cars, and even in baby food. Applications on Earth of technology needed for spaceflight have produced thousands of spin-offs that contribute to improving national security, the economy, productivity, and lifestyle. It's almost impossible to find an area of everyday life that's not been improved by shuttle program technology. In the fields of health and medicine, technology from the shuttles have helped develop infrared ear thermometers, new designs for artificial limbs, and light-emitting diodes. In transportation, improved radial tyres and new icing systems. Advances in video enhancements, digital camera sensors, and even landmine removal techniques have helped criminal justice and saved lives. New ideas for water purification and the cleaning of polluted materials have helped environmental concerns, as has better mining practices and food safety systems developed by NASA. In the consumer market, temper foam and freeze-drying technology has been essential to modern living, and new advances in enriching baby food has helped children worldwide. These incredible contributions made by NASA's Space Shuttle program have changed our lives and cemented the shuttle's status as a design icon. NASA's current plans call for the Space Shuttle to be retired from service in 2010, after nearly 30 years of service. Atlantis will be the first of NASA's 3 space shuttles to be retired as the program nears its end. To fill the void left by the shuttle's retirement, a new spacecraft is being developed to ferry not only passengers and cargo to the ISS, but also to travel beyond Earth orbit to the Moon and Mars. The Orion spacecraft and the Project Constellation.
The Orion spacecraft is America's next manned spacecraft. So the vehicle is going to be capable of low Earth orbit operations and also capable of going beyond low Earth orbit. This new spacecraft design takes advantage of being able to do both. It's a very flexible design.
So we're now looking at a process of human movement out into the solar system, which has more than just technical implications. It has sociological implications in terms of technology development, in terms of inspiration of youth, in terms of demonstrating leadership in the world, in terms of creating new opportunities for economics and economical development in space, and scientific implications.